Right, good morning. This is Friday's lecture. So our agenda for today is to finish off the example on Brittle criteria. Then we're going to start a new topic, which is design analysis of beams. Specifically, we're going to look at shear force and bending moment diagram. And I have an announcement to make. And on March 24th, there'll be a quiz at 9:30, and you'll finish off at 10:20. So it'll be a quiz, and this quiz I'm going to simulate how the exam or simulate the examination condition. So you do a quiz. Okay, the quiz will be open at 9:30, and you have to submit by 10:20, and failure to do so will award a 0 mark, okay, for the quiz. Okay, so I want you to get used to it. If a question is 50 minutes, okay, so the duration of the quiz, no doubt it says 50 minutes. Okay, well, I suggest that you work on the problem. So 50 minutes, 40 you work on the problem, solve the problem, or attempt the quiz. You take about 40 minutes, including checks. Okay, and then scan or take picture, upload. It take about 10 minutes. Okay, so that's what's going to happen on March 24th. Okay, I want you all to get used to it, because this is what's going to happen in the final exam. Okay, I want you all to start practicing. The question will not be too difficult. Later, I'll post homework. Question will come out from the homework. Okay, try to do it. Okay, the question will be similar from the homework, and then you'll upload. Okay, I want you all to get used to it. More important thing than anything else. Okay, right. So now we're going to continue on our example, right? So yesterday we are trying to solve this condition of the element, where given there's a brittle material and they have an ultimate tensile, ultimate compression. So this is the loading condition. We are going to find where the structure failed. Okay, we don't know. So just to quickly recap, we're going to use Mohs criteria for brittle material. As you can see, for brittle material, it can withstand higher compression than tension. So the way to do this is to find stress A, stress B, and it's based on plane stress condition. So we know that the formula that we're going to use is stress A over stress ultimate tensile minus by stress B over ultimate compression. Okay, and if it is greater than 1, or this thing is greater than 1, structure will fail. And if it is less than 1, structure will be safe. Now it will not plastically deform because it's brittle, right? Okay. So oh, we will go plastic region. No, not for this case. Okay. So we have drawn this. So I was going to complete the 3D mold circle. Excuse me. So you ask me, Eugene, why do we have to complete 3D mold circle? Okay, I know it's obvious now, but we know that this is a 3D element. Okay, where stress Z is equal to 0. And we want to make sure that this is our stress A and this is our stress B, not point Z is on the outside. Okay, or if the circle is shifted, right, a stress A can be at point Z. Okay, so the next circle that we're going to draw, right, so this is our next circle, somewhere around here. Right, so this next circle, so this first one, the biggest circle, this is, we know, our XY plane. And then the circle that I just drew, right? X is nearer to this smaller circle. So this is XZ plane. And finally, on the last circle, a big one. So this is so this is a bit, I think it's about here. So this is our last circle. Okay. So this one belongs to our YZ plane. Okay. So from here, we work out. We have to find. Okay. So from here, we have to find we're going to find our stress A and stress B. So I don't think we've done that. Yes. So we have to find stress. So find stress in. So we have to find a center of circle. So that's correspond to our stress average. So as you can minus 15,000 plus by 2,000 divided by 2. So this will come out to minus 6,500 psi. Okay, so minus 6,500. So that's about right. And then we have to find what is the radius of the circle. So this is based on tau max. Okay, so this will be equal to, so the shear is 9,000 squared, and then the radius, right, will be 2,000 minus 15,000 divided by 2. Okay, so where you see this 15 minus 15,000 is what we have for the distance from here to here. Okay, the distance from here to here. or the distance from here to here. Okay, so this is correspond to our or you want to call it 2000 minus 15,000 divided by 2, right? So this will come out to be equal to 9,000 squared, right? So this will be equal to 379.4 psi. And then from here we can calculate our stress A and B. So this is equal to minus 6,500 plus or minus 12,379.4. So one side, so minus 6500 plus 12379.4 will be 5879 psi, and the other one will be 18879.4 psi. Okay, so that's our stress A and stress B. So now we have to find where the structure fail. Okay, so we want to know now. Okay, so we're going to use stress A, right? So stress A is equal to 58. So we call stress A is equal to 5879.4, and then stress B, so minus stress B is equal to minus 18879.4. So if we were to construct, okay, we were going to construct our Mohs operating bracket, right? Remember we have a graph like this, you guys. So this is our stress A, stress B, and we have a diagram something like this, right? Very similar like this. So we want to find, right, our situation, is it in here or outside here, right? When it's outside here means the condition is greater than 1. If it's inside here, our condition is less than 1, right? So now we put in our value. So we have stress A. So the formula that we're going to use is stress A over stress ultimate compression, ultimate tension, minus by stress B over ultimate compression. Okay, so this will be equal, so stress A is equal to 5879. Okay, let me move this further. So this will be 5879, and then divide by ultimate tensile is 10 times 10 to the power 3, and then minus, you have to include your minus sign down here, and then the compression over here, you just put the magnitude, which is 30,000. So this will be equal to, 5879.4 divided 10 to the power 3 is 0.58, or 0.588 plus 0.6293. So this will be equal to 0.588 plus 0.6293. So this will be equal to 1.2173. Unfortunately, when there's a case, structure will fail. Okay, because the stress A over stress UT minus by stress B, because of stress A over stress ultimate tensile, right, minus by stress B over stress ultimate compression is greater than 1. Okay, so that's why the structure will fail. So we have just covered 3 criteria. So with these 3 criteria, we can design our structure. So the 2 criteria that we have used is for ductile material, and Mo is for brittle. Okay, so I'm going to stop here now. Then we're going to start on a new lecture on design analysis of beam. And remember, March 24th. Okay, I want to train you to get used to the anxiety, not to be so anxious for your exam, because in the exam you have fixed time to upload your videos. I want you to have that time, okay, to make up that time. Thank you. See you later.